So welcome to my talk. This is a talk about embeddings and vector databases, which is, of course, a hot topic right now. It's one of those AI topics. It's about AI stuff. And I kind of have a personal mission when I talk about AI things. And because it's easy to assume some things about what you need to do all this AI stuff that's very popular right now. And assumption number one is that it has to be in Python. Assumption number two is you got to use some cloud thing because you couldn't possibly have enough power in a MacBook, my 5-year-old Intel-based MacBook using its CPU, not its GPU, to do anything real. And that you have to plop down a credit card to pay for these things. And I think that is crap. And so I have not used Python. I have used TypeScript. I realize I'm using TypeScript at a Java conference. Don't at me. Yeah. I have used Hugging Face transformers, which technically are downloaded from the cloud the first time and cached. I could download them manually and configure it so that I don't have to do that, but I was a little bit lazy. So it's not using a cloud service, and it's all free. So I'm using, for my vector database, I'm using Redis running locally. As you might have guessed, I work at Redis. So of course the demo is going to be in Redis. But the vast majority of this talk is going to be the ideas to get you to get an understanding, an intuitive understanding of these things with those three principles that I just laid out. So, my name is Guy Royse. I'm a developer advocate at Redis. I like to joke that there are three things on this slide that matter. There's something that matters to you, there's something that matters to me, and there's something that matters to my boss. The demo is in Redis. We work at Redis. He wants you to know Redis is more than just a cache. You can do cool vector. You can use it as a vector database as well, among other things. Who here has used Redis before? Yeah, that should be just like everyone. Has anyone used it for anything other than a cache? Exactly. I saw 3 hands go up. So that's what he'd like you to know. And frankly, I'd like you to know that too. I have some equity in the company, and I'd like to turn into a pile of money if you would all help me. The thing on here that matters to me is the social links there. You can see I'm on Blue Sky and Twitter, currently known as X, and I have a blog at guy.dev. So give me a follow on those things. I measure my worth as a human based on how many people follow me on social media. My wife told me that's one way to live your life. And the thing that matters to you is the GitHub URL. So the demo I'm going to show at the end of this talk will involve a camera and finding a meme twin, and it may involve a volunteer from the audience. So if someone wants to find out who their meme twin is, they can. And we'll run this in the Redis booth after the talk. So if we run out of time, everyone gets to go, right? But that GitHub has all of the code for the demo, and you can literally clone the repo, run Docker Compose up, and find your meme twin. It just works. So that's what we're doing today. A caveat as I talk about these things: I am not a data scientist at all. I'm a developer. I've been writing software for a lot of decades, more decades than I'd like to admit. And I'm not even particularly mathy. Through happenstance of education, I never took calculus. And so a lot of the math behind data science is just stuff that I don't know how to do. But I am a fan of data science and all these technologies. And so I go in and I learn about things, and I get excited and I share them. And honestly, I think for every developer in this room, you don't need to be a data scientist to use these tools. Data scientists built the tools we're using. We're developers making use of them. I like to think of it as we need a mechanic's understanding of an engine, like in your car, as opposed to an engineer, like a mechanical engineer's understanding of an engine. Mechanic understands how the motor works. They understand how some of the principles of it, but they would not be able necessarily to build an engine from raw steel. They wouldn't even know which steel to select necessarily. They might, but it would be sort of it's also kind of like the difference between like a structural engineer versus a carpenter. Framing a house, they follow the rules, they use the thing. They use the tools that other people have built for them. And we're kind of doing that as developers here. So I'm not a data scientist. Is anyone here a data scientist? A couple of you? So just only 2. So don't listen to them. I'm actually something of a data scientist myself. And so you should believe everything that I say in this talk. So I've got four main agenda items. Is four a lot? Well, that depends on the context. At a conference talk, not at all. For a conversation with your boss, probably. Those agenda items are first covering what the heck is an embedding. My goal here is to not to give you a mathy explanation of what an embedding is or how to use them, but an intuitive understanding of what an embedding is. And to do that, I'm going to tell some lies, but I'll call them out when I do. To get the, it's not a lie, it's a metaphor. I'm told that analogies are like metaphors. But we're going to talk about what an embedding is. And then we're going to talk about how you can use embeddings to solve interesting problems. How we can make embeddings. I'm going to go off on a little bit of a tangent in the middle of the talk, partly because I need to fill 50 minutes of time. And so I'm going to talk about a way that you can build your own models, to build your own embeddings from scratch, and then tell you that you should never do this. And I'm going to use convolutional neural networks to do that because for two reasons. One, well, for probably three reasons, for a few reasons. One, it's the one I understand. I don't know how to build a transformer using Keras from scratch. I'm sure I could learn, I just haven't gotten there yet. And so I use convolutional neural networks. But the goal here isn't that you should use convolutional neural networks or transformers or build these things yourself. It's mostly so that you can understand that it's knowable. I have this book that I got. I don't use it anymore because my kids are grown up, but when my kids were little, the book was entitled 50 Dangerous Things You Should Let Your Kids Do. Fantastic book. It included things like play with fire, climb a tree, sit on the roof, use a pocket knife. Maybe that's an American thing, I don't know. They didn't have fire gun in there, don't worry. And most significantly, though, was take things apart. And so if a kid takes apart, say, a dishwashing machine, because it doesn't work anymore, they're not going to learn how a dishwashing machine works by taking it apart necessarily. But they're going to find pieces in there that are knowable, that they do understand how they work, and they learn that they could learn how the dishwashing machine works. That's the goal of what I'm going to do when I talk about how to use convolutional neural networks to make embeddings. Is to show the knowability of it. And then last but not least, we're going to have a code and demo. So let's start with the first thing. What's an embedding? Am I the only one around here that knows what embedding is? So one of the things I did here is, for these memes, is they tend to be low resolution, right? Because they're from like standard definition television captures. So I put them into Photoshop to upscale them, and then I had it do AI fill-in on the sides to create a 16:9 ratioed image so it would look nice here. And I think it's really funny that the AI decided that we needed another rifle barrel on the right side of that image. Actually, this is how all bowling alleys are in the United States. No, I found that rather amusing. And in order to talk about embeddings, I want to talk about two types of data. There's structured data. This is this data that we've been using our entire careers. It's the numbers and the strings and things like locations and structures, and it's that data that we've been, it's integers and floats and bytes and these things. They're very, very structured. We know exactly how to deal with them. They're deterministic. This is the data that we've been using our entire careers. This is the data that everyone has been using forever. It's the default. It's what computers are really, really, really good at. And then there is unstructured data. This is data that humans are good at, but until recently, computers have been not so great at. This is things like text. And I'm not talking about full text like prose, although I am also talking about that. You can do full text search, which is a way of doing working with unstructured data, but that full text search is limited. It's basically keyword search with some add-ons. So it can find it'll match give to gave and things like that. But it's fundamentally a keyword search. But unstructured data that's text is going to be things like, I have a paragraph where I'm talking about, let's go with fast food restaurants. I always like to use the fast food restaurants example. You've got some restaurants which, say you want to find all the documents that reference a fast food restaurant. And one says Burger King, and one says, are there Taco Bells here now? I think there's Taco Bells here. Does anyone like it? One, yeah. I predict they're not going to do well in the UK. Or KFC. We know as humans that that is a fast food restaurant. But keyword search isn't going to find that because it just is going to look for the word fast and food and restaurant. And so unstructured data is harder to work with. AI models will let us work with this tool. Images are another great example. It's very easy for humans to say there's a kitten in this picture, and there is a ball of yarn in this picture, and there is an adoring human looking over the cat and being amused because the kitten is playing with the ball of yarn. Computers have trouble pulling this out, or did. And audio is another example. But it's this data that is easy for humans and hard for computers. Structured data, we know what to do with structured data. We've been using it our entire career. Structured data is anything that can go in a where clause in a SQL statement, right? Where, clue greater than 0. And so what we do with structured data, of course, is we store all of our company's structured data in SQLite. This is a solved problem. Just use SQLite. If you're, maybe you don't use SQLite at your company, maybe you use something a little different, you could always store all your structured data in Access. But maybe you're like most of the companies out there, and you store it in Excel. But structured data is a solved problem. We know how to solve it. But how do we take unstructured data and turn it into something that we can do computing against, that we can operate against? Well, there are a whole series of models out there that have been created by data scientists that are smarter than me that can take unstructured data like text and images and turn it into arrays of numbers, which we call embeddings. And so I'm a JavaScript developer, so don't need to debug your code if it doesn't compile, right? Think about it. So, for example, we could take text, and in order to make text into something that you can do math against, that you can compute against, you would run it through perhaps an LLM to summarize it. Many of the models that will create embeddings from text have a token limit, size on their token limit, and the text might be too long. And so you could condense that down to make it fit into the token limit of that model. You would then tokenize it. And the tokens are things like words, but it also can be prefixes and suffixes of words. It could be punctuation. And if it's like an acronym, it could be all the individual letters. And so, for example, NASA could be made up of the tokens NASA. Whereas the word precompiled can be made up of the tokens pre, compile, and ed. And so, because these are meaningful to the model. And so you take that text, you tokenize it. And by you, I mean your software. And by your software, I mean the libraries that we're using. And then that is run through a model, which creates an embedding. And it spits out a pile of numbers. And this is just a simple array. In the case of a lot of the text models I've used, I think it's an array of 384 32-bit floats. You can do similar things with images. You can transform them to make sure that they're precisely 512 by 512 pixels, whatever the model requires. In the example I'm going to show later, you could do convolutions to then find patterns in the image. And then you run this through a model to get the embedding out. And again, you get a pile of numbers. So there are some models that are very clever and can actually do both of these and get similar embeddings. So you have a model that can both take text and turn it into an embedding, and images and turn it into an embedding, and those embeddings are similar. So what are these embeddings, though? What's in them? What do these numbers mean? Well, we're going to pretend that we have a really, really simple model. And all it does is it finds it puts out two values in its embedding. And these values are a feature that the model has detected in the image. So the AI model is looking at it, and the first number is something to do with one thing, and the next number is something to do with another thing. And we really don't know what these values are. We know that the numbers are similar when you give it similar images. And so, but we're going to pretend that there's only two axes instead of like 512, and that one of them is elderliness and one of them is alcoholic. Now these could be, like I said, this could be whatever the model thinks is appropriate when it was trained. And that could be, one axis could represent, one of these values could represent the catness of a thing, and the other one could represent whether there's fabric in it or not. And maybe one has a sense of age. And in this case, we're pretending that we have elderly and alcoholic because these seem to be topics in memes. And so here we have Leonardo DiCaprio with a coupe glass, giving a good cheers. And in this picture, Leonardo DiCaprio is not particularly elderly, and so he's slightly below 0 on that ranking. In my example here, I'm using -1 to +1. This is sometimes what's used. Sometimes it can just be 0 to 1. And then on the right, we have an alcoholicness, and he's got a coupe glass, which is clearly for cocktails, and so he's probably drinking. And so he ranks high on alcoholicness. So these numbers that we get back are scores showing how much or less of a thing that particular theme for that value is. Another image might have other results. Grandma discovers the internet, probably my favorite meme. And grandma is clearly very elderly, and so a high score there. But there's nothing in the image that suggests that she's an alcoholic. Your grandmothers may vary. I just know that when my grandmother would make blueberry pie, it tasted like it had something else in it. But again, these are scores. And so what you can do then is you can take a whole bunch of images and get their scores for all these traits. And so here we have 3 popular memes: Success Kid, the most interesting man in the world, and mocking SpongeBob. And then we have this unlucky chap, and we can create an embedding off of that. And then what we can do, a simple thing we can do, is we can see which pile of numbers is most similar to the other pile of numbers. Are the numbers in the image of me most similar to Success Kid? Probably not. Most similar to the most interesting man in the world? Well, I'd like to think so. Or most similar to mocking SpongeBob? Probably correct. Of course, the model is going to spit out and says, "Oh, look, middle-aged guy." Right? Literally middle-aged guy, I guess. And so you can compare these numbers. And the more similar they are, the more similar the things that generated those numbers are. And I used 2 axes, or 2 values, because to show that you can represent these as latitude and longitude, as an x and a y. And then you can plot them out on a graph. And so you can see that we sort of have quadrants here. On the top right, we have young alcoholics. Actually, I take it back. Grandma discovers the internet is not my favorite meme. That drunk little baby is. And so you've got on the top right, or the top left, I got my stage right, my screen right backwards. But you've got Dos Equis man who's drinking a beer, but he's not like, he doesn't have a cocktail, right? But he's clearly older than Leonardo DiCaprio. And in the bottom, you have some old people, Bernie Sanders asking one more time for, something. Grandma discovered. And then on the bottom, you got Success Kid and the why not both girl. Porque no los dos, eh? And so we can look at these and we can kind of see that they're closer. We can see similarities. There's clustering and grouping here. And the math that we do to determine how similar these points in space is basic geometry. So an easy way to do that is with Euclidean distance. It's literally draw a line between the 2 points, and whichever line is the shortest, the shorter the line, the more similar they are. It's that simple. And so it's just a matter of, I want to search a bunch of vectors, I've got all the points, I calculate the length of all the lines, and I pick the shortest. Now obviously that's slow, and so there's indexing and stuff to make that faster. Another option is cosine similarity. You take the angle from origin to the 2 points that you want to compare, and the more narrow the angle, the more similar they are. You take the cosine of the angle. That's why it's called the cosine similarity. And these both work because towards the middle of the graph here, this chart, things tend to be more generic. If you think about like the rank of not alcoholic, very alcoholic, you kind of get like midland alcoholic. And for elderly, you get old and young on either side. But in the middle, you get someone who's just sort of average aged. Someone in their 30s probably. And what can happen is more general concepts end up closer, and more specific concepts end up further out. And so cosine similarity can be useful because if I want to find fast food restaurants, Burger King and KFC and let's use Burger King and McDonald's specifically. They're going to be further out, but very close to each other because they're both fast food restaurants and they're both hamburger joints. Whereas fast food restaurant might be further away. And so they would match each other before they would match with fast food restaurant. But they're going to be on the same axis. And so you can use cosine similarity to find things that are on the same axis. And you can use Euclidean distance to find things that are close. And if you want to kind of split the difference between those, you can use an inner product, which I don't have a good graphic for because it doesn't neatly lay out in the same way that these do. Another option is you could find things that are just nearby. And maybe they're there and maybe they're not. And so you can do a radius query. So we got grandma discovers the internet, and we want to find out what's nearby and find that Bernie is kind of nearby. This can be used, actually good for caching, to say, is there a thing that is close to the thing that I'm looking for or not? If there's not, maybe I go to some other system, look it up, and then I cache it. And then next time I want it, I can return it. So that's what vectors are and sort of how you can query them and use them and compare them. A vector database then, or that's what embeddings are. A vector database, all these embeddings are vectors, but not all vectors are embeddings. In a vector database, you take embeddings, or any vector really, and you create them on images, and you load them into the database. So with all their ancillary data. So here's Success Kid with the photo and the embedding. Here's the most interesting man in the world with the image and the embedding. And here's Mocking SpongeBob with the image and the embedding. And then you can query this database based on vectors. So you can search images with images. Or if you have a model that generates both text or images from input and gives similar vectors, you can search images with text, which we're not going to demo today. We're going to demo the image with image. When it comes time to make indices to make this perform, you've got two primary choices. There's flat, which is a simple brute force search. Creates an index and it's perfectly accurate, but it's brute force. And so you will run into scaling limitations with flat after a while. In Redis specifically, the rule of thumb is if you have about 1 million vectors, you should consider moving away from flat. So if you have hundreds of thousands, you should be fine. HNSW stands for Hierarchical Navigable Small World, which is hard to say. And the idea with HNSW is that you have a layer of graphs of a subset of all the nodes in our little thing where we have the two axes with elderliness and alcoholic. You take a random sample of that and you search that first. So it's a smaller version of the larger database, the larger vector space. And then you find the closest one, and then it points to another layer which has ones that are close to it, and to another layer which has ones that are close to that one, and you walk down this hierarchy until you find it. And this is not perfectly accurate, it can be wrong, but you can adjust several parameters to say, I want it to be more accurate, or I want it to use less space, or I want it to be faster. And so this is what you need to do when it's time to scale. There are three use cases I'm going to point out here. I think there are other use cases, but I'm going to point to three of them. The first one is kind of a thing I've talked about already. It's semantic search. The idea here is that you have Redis or some other database full of content and embeddings. And so in this case, I've got text embeddings. It's various meme text, and I've got the text itself. And so we got deletion as 100% file compression. It's one way, but it's totally 100%. You've got TypeScript is just JavaScript for C# devs. Changed my mind. And code doesn't compile, compiles it again. So these are the things we put in our database. We want to search on them. And so we find we have a text of don't need to debug your code if it doesn't compile, and we want to create an embedding from that. And then we can search that embedding against the embeddings in Redis, and then find the closest match. So this is the the sort of the bog standard use case for vector databases. Another one is semantic caching, which I kind of touched on a little bit too when I was talking about the range query. The idea of semantic caching is you might want to cache something that's slow and expensive, like an LLM. So using an LLM is kind of a slow process. It adds up quickly, and if you could cache similar questions semantically, you could save a lot of money and get a lot of performance. So Grandma is here searching on the internet. She's on some chat bot, and she heard her nephew say something about dank memes, and she doesn't know what a dank meme is. Can you explain to me what a dank meme is? And we could ask the LLM, but before we do, we could hit a cache and see if anyone has asked this question before or something similar, and then return the cached response from an LLM. So we take the question, we turn it into an embedding, and we hit the database. And we say, are there any things here that are similar? Has this question been asked before? And there's what is dankness, and I don't understand what memes are, but none of those really match because they don't hit both the dankness axis of the question and the meme-ish axis of the question. And so that's a cache miss. If you got a cache hit, you just return the result. But there's a miss, and so we ask the LLM the question instead, and then we return the result to Grandma, and then we shove it into the cache, and then if someone else comes along, they can get that question answered without hitting the LLM. This is great. The better example, I use this example on the slides because it matches the theme of the talk, but a more common example would be, why are my photographs blurry? Why are my pictures out of focus? These are exactly the same questions stated differently. The embedding knows that, will create, or the model knows that will create embeddings that are similar, and then you'll have a score that's close, and you'll be able to get a cached answer to that. So that's semantic caching. I think this is particularly powerful. Of course, you've probably all heard of RAG by now because everyone talked about it a ton last year. The idea of RAG is it's retrieval augmented generation. This can work well with a vector search with embeddings, although you don't have to use it. The idea of RAG is that Grandma has the same question. She doesn't understand what a dank meme is. She's talking to an LLM, but this particular LLM it doesn't, for some reason, know what dank memes are because it apparently wasn't trained on data from the internet. And so we can go and query a vector database with the question and get context. And that context about dank memes is then handed to the LLM along with the question. So that's the idea of RAG. Now the LLM is doing the generation. It's augmented with outside data. This is literally as if you had typed, here's a paragraph about a topic, now answer this question reusing the paragraph I just gave you. It's like you went to ChatGPT and literally typed that in. This doesn't have to be, though, the retrieval part doesn't have to use vectors. You could totally go to a relational database and pull down customer information and give it to the LLM and saying, given the following customer information, answer these questions about the customer. So the retrieval is the important part here, not the vector search. But it does work nicely with vector search. This also works nicely with semantic caching. So you could put a caching in front of this so that you don't even have to ask the question more than once if someone's asked it already. And then, of course, the response goes back to Grandma. So that's pretty much it for embeddings and vectors. I'm going to go off onto a tangent here and talk a little bit about neural networks. Some of you have probably heard some of this material before. And I'm going to talk about CNNs and how they work and how that they can be used to create embeddings. And again, this isn't necessarily that you should do this, although, well, you should totally do this and play with this. You should totally not put this in production. I believe 3 people raised their hand when I said who was a data scientist. The rest of us aren't. And data science is hard. You want to stick with the code stuff and work with a data scientist when you're building custom models. But I'm going to show you how to build a custom model in principle anyhow. I have a talk that I did a few years ago. I think I might have done it here actually in like 2018 or 19 called Deep Learning Like a Viking. There are recordings out about online where I go into details of how you can create a convolutional neural network using Keras. It might have been before Keras became part of TensorFlow. I don't remember. But this is some of this materials from that talk. If you want to actually build something like this, you can go out and use that. But we're just going to look at it so we can know that it's knowable. So this is your basic neural network. We've probably seen this picture before. Probably everyone here has seen a picture like this. It is, in essence, a function. It's got an input layer, and each of these inputs are floating point numbers. Those numbers cascade down to another layer where math is done upon them, and transformations occur, and then you get out new numbers. And the numbers and the math that happens inside here are set or programmed using you give it training data that's labeled, and then the values inside of the neural network get updated as through a process called backpropagation. I have learned to parrot the words stochastic gradient descent. These are words I can say. I kind of know what they mean, and I've seen some pictures, and I have a vague conceptual understanding of it. But all I know is that what I really do is I call model.fit, and then it does it. But this is your basic neural network. And you can, like I said, you can think of this as a function. Numbers come in, numbers go out. The neurons that make up this neural network can also be thought of a function. They have an input, an x, and an output, y. And so you could plot this out on a graph. The input has a weight associated with it. This is a number that is given to it through the training, through the backpropagation, through that stochastic gradient descent. And it has a bias, again, number achieved in the same fashion. And the basic function that this neuron has, and this is not a realistic neuron because it only has one input. They should have several, but this one is one just for teaching purposes. But the formula here is the input times the weight plus the bias gives you y. And if you remember algebra, this is the actual function, y equals mx plus b. This is a function to draw a line with a slope and a y-intercept, so an angle, and then slides it back and forth. And the neural network is made of a whole bunch of series of these. But there's a problem with that, which is that if you take a linear function, say one neuron that puts out a linear result, and feed it into another neuron, which generates a linear result, you're only going to get lines out. And so if you could only draw straight lines with a complex neural network, it's not that complex. It doesn't solve that many useful problems. Most problems aren't straight lines, as much as we want them to be. And so to solve that problem, each neuron in the neural network gets what's called an activation function. That activation function is applied to the output before, well, its output. And so it's y equals mx plus b passed into a function. There's several functions here, and I totally confess to, I said this was a sigmoid, which is technically true. Someone called me out on this Monday night when I gave this talk in Sheffield and said, well, this is technical logistics function, and it's sigmoid because it's S-shaped. I'm like, okay, fine. I'm not mathy. But the idea here is that you could run it through this function that would take the output, and instead of having really big or small positive and negative numbers, you get a number that approaches 0 and a number that approaches 1. And it sort of constrains it down a little bit. This isn't used a ton anymore. There's hyperbolic tangent, which also isn't used a ton. Same idea, except it's -1 to +1. It's kind of a tall sigmoid. And what everyone uses instead is ReLU, because it works. I think ReLU is actually the most pretentious name for what this is. Because what it really is max x comma 0. That's all it is. That's all this function is. But it's rectified linear units, and then it was long enough that we needed to abbreviate it. It's almost German. But the idea is that if you start giving these functions for the activation function, or using these activation functions, your outputs aren't straight lines anymore, and they start curving and solving more complex problems. And so that's the big value of using these. A more realistic neuron has multiple, this is a more realistic neuron, it's still not realistic, but it has multiple inputs. And the math is essentially the same. It's the input, the sum of the inputs times the weights plus the bias, or to use a sigma. So that's neural networks in 5 minutes. I hope that was 5 minutes. Let's talk about convolutional neural networks next. A convolutional neural network is a special type of neural network that is partially connected that's really good at hierarchicalizing images. So you give it an input image at the first layer, and it's literally just the pixels in the image. There are a series of filters that are applied to that image to find patterns. And so a filter might be a line going from the left to right, or it might be a line going up and down. And these filters are applied to the image, and then you get an output, which is a map of everywhere where that filter matched. Those outputs then show you where all the horizontal lines are at, or where all the vertical lines are at. And then you can run those into another filter. And then it finds where you got the pattern where there are 3 horizontal lines down the middle, or 3 vertical lines along the top, or maybe there's a diagonal line. And then those become shapes. And then the shapes become things like eyeballs. And the eyeballs become things like faces. And then it hierarchically decomposes that image. Pooling is a way of compressing it down to make it a little easier for the model to not fixate on small details that aren't necessarily relevant. Like if the line's got a little bit of a jog in the middle of it, the model might think that jog is important. When it's not, it's kind of like squinting. And then the output of these final pooling layers is flattened out to give you a set of features that have been identified in this image. So this pooling layer says that there is a cat in the image, and this pooling layer puts out information saying that there's a dog in this image. And then you get these flattened output. It's sort of the features. It's the embedding. In a full CNN, you then feed these into another fully connected neural network, and it will classify them and tell you what's in there. But for using it for a embedding, you just strip that outer layer out. Here's a better picture of sort of how filters work. Here we have my attempt at a stick figure troll face. And then you can see here, we've got various filters and how they map the output. In particular, I like the one in the top right, up here, because that matches the eyes, and this just looks like a pair of eyes staring at you, doesn't it? So it found all the eyes. The eyes have it. The searching for this filter is it's a pan and scan sort of thing. So we'll look at a little 3x3 thing here, because that's how big the filter is, and it just goes across the image, finding matches eventually. There we go. So that matches the filter, and so it generates an output. This one doesn't, this one doesn't, this one does, etc. And then you get, I really need to automate the last bit of this because my point's been made. There we go. And so the idea is you create a map of everywhere that filter occurs. That's what the output is. But this is a simplification. It's a lie. These are actually numbers. And even this is a bit of a lie because the numbers aren't going to be neatly 0 and 1. They're going to be floats from 0 to 1. But 0 and 1 fits better in the little box. And so these inputs are numbers. The filters are numbers. The output are numbers. And you can see that when we look at this on the image on the right up there, it partially matches the horizontal line, but not fully. Whereas the eyes, it fully matches it. So you sort of get all the horizontal elements of the image. And these numbers here are the pieces of the y equals mx plus b and the activation function. And so the image is the input. We take the sum of the weights, which is the filter, and add the bias, and then we run it through ReLU, and we get an output. Pooling is actually really simple. I'm using a max pooling here. The idea is you go through any section and just compress them down. So there's nothing in here, there's nothing in here, there's something in here, and so we mark it in the next image. Something in here, we mark it in the next image, and then the rest of them are ignored. This doesn't overlap like the convolutions do. And again, these are numbers, not just Booleans. And so that output that we got earlier generates a pooled version that almost kind of looks like a troll face if you squint a little bit. So then you take the output of all those poolings, and then you get numbers that represent the scores for the embedding. So this is how you can use a CNN to build an embedding. I think it would be a fantastic experiment for someone to try, but don't put it in production without working with a data scientist. And just to reinforce that, we're developers. We want to chase the new thing, right? This is actually a bad way to live your life. Don't do this. Don't do what the meme is saying. Do what the text is saying. If you want to go build a custom embedding model, do it, play with it at home, learn from it. It's a great way to learn. If you want to do it in production, make sure you work with a data scientist because there's gotchas that you aren't expecting. So we got, we've got about 10 minutes left. So I think it's time to do a demo. So let's go ahead and get the demo going. Shout out to Chappelle, he made it into 2 slides. He's from my home state in the United States of Ohio, so extra props to him. And of course, my demo, well, I'm not saying I'm going to use Redis, but I'm going to use Redis. I've built a fairly simple application. It's just a semantic search application. I'll show you how it works here, and then we'll get it running, and then we'll get a volunteer from the audience to see who they are and what meme character they are, and then we'll take it to and then I'll take it back to the booth, and we can do it there as well. So we've got Redis here in the middle, and I've got a TypeScript library that I've named meme loader. And what it does, first and foremost, is it goes to Redis and creates an index, sets it up as a flat index, for vector search. And then it loads a bunch of files off the file system, where it's got the file name is the title of the meme, and it's just the images. And it creates embeddings out of all those images, writes the bytes of the file, the embedding, and the title all out to Redis. And then we have Redis is now full of vectors. I've got a whopping 72, so this performs just fine. Client side to use this, I've got a meme client. This is just a simple web app written in vanilla.js. The hardest part of this app was getting the camera to work. You'll find when I do my demo, I'll have to unplug the HDMI cable and plug it back in to get the camera to work because technology is fun. But its purpose is to take that picture and send it to the server. The server then will create an embedding off of that photo, use it to search Redis, and then use what it finds to fetch the title and the image bytes, and then return that to the client. A thing that I could have done in this application, I probably should refactor to do this, is this TypeScript code that I'm writing will run in the browser as well as on the server. So the server is running Node. The client, however, the Hugging Face transformers I use will work in a web browser as well, or as we like to call it these days, the edge. But it's a great way to save some compute resources is to use someone else's GPU. So let's go ahead and take a look at the code and demo. Yeah. Maybe this is my favorite meme. Okay. I've got the code up here, and I'm going to show you a little bit of the code. It's code in a tech talk. Its purpose is to show you that it's knowable, and so you can see what's involved, not to memorize the code, because I've been to a lot of tech talks, and no one remembers the code anyhow. But I want to show in particular this file here, because this is the file that creates the embedding. And you can see what's involved in it. There's not a lot of lines of code here. This is a commented and well-formatted piece of code, arguably. I think it's great because I wrote it. But it's only 16 lines with white space. We're bringing in Hugging Face transformers, which is a free library. It will download models off of Hugging Face automatically for you. And you can use them to do embeddings and to do LLMs even, and one-shot classifications of images and all sorts of things. There's lots of models on there. A lot of them will run in TypeScript, and you can run them in a browser or in Node. And it exports a function called pipeline. What pipeline does is it builds, well, a pipeline for whatever purpose you want. That purpose is the first argument here. So I'm building a pipeline to extract features from an image. And the model name that I'm using is this one here. This one actually does text and image feature extraction. And then it needed a little bit of extra parameters just to say that it works with 32-bit floats. What this pipeline function does is it builds up everything you need to download and transform and embed that image. And so it literally creates a function that you hand a URL to. That could be a file path, it could be a URL on the web, it could be a data URL, and it will resize it and embed it. And so then I have a little function here that takes that string, calls my function that I created with the pipeline, which is extractor. Tensor has a data property on it. That data property is the embedding. It's the 512 floats that make up the embedding. I then annoyingly need to take the raw bytes, the buffer of it, on line 10 here, and that buffer, because I'm working with Node, needs to be turned into a Node buffer before I can hand it to Node Redis. And so I have to take a buffer and make it a buffer so I can pass it in as a buffer. Yo dog. I don't have any yo dogs in I should totally have a yo dog meme in my slides. And then I just return that Node buffer, and that's all it does. The Redis code here, we're getting a little short on time. I'll show you how you can create the indices. Go check this code out when you get a chance, and I can show it in the booth if people want to get into the details. But the key thing here is that you use the ft-create command to create an index, and you give it all the fields in Redis. This is stored. These are stored as hashes in Redis, and you say that the field in the hash that is title is text, and you can do full text search on it. The field that named embedding is the embedding, and it's a vector. We're doing flat as opposed to HNSW. It's got a 32-bit float. There are 512 of those 32-bit floats in there because that's what the embedding puts out. That's what the model. That's what the embedding looks like that the model creates. And then I can specify a distance metric here, which I use a variable for. To match, we then build a query up here, and then we pass it in. And this is, I don't think I have enough time to go into this code, so I'm going to skip over this. But the key thing is you call ft.search in Redis, passing in your query and any options. I think we need to run this code. Do you agree? I see nods. Okay, so Docker compose up. Moment of truth. Okay, come on. There we go. I'm like, no, don't download. We're on conference Wi-Fi, that's terrible. Okay, good. The meme loader is running and creating embeddings right now. Now I'm creating 72 embeddings. Takes a couple seconds because I have a 5-year-old MacBook Pro and I'm using my CPU because I don't have GPU support for any of these libraries. But still, it ran pretty quickly. So this is now running. I got a browser open already. Let's go to localhost 8080. Nope, that's the API. 8000. We'll see. No, we're not going to use OBS. Okay, yeah. Okay, so this is the part where technology is fun. So I'm going to unplug the HDMI. Wish me luck. Pray for me. Okay, it's working now on my side. And now I should plug back in, and it should be working. Am I on there? It looks like I'm on there. Wow, the interference is awful. So the app is pretty simple. I take a photo. I can choose down here which distance metric I want to use. Let's start with cosine similarity. Actually, let's start with Euclidean distance. I think that's the default in my app. I can't remember. But we're going to click Use. And there I am. Accurate. Let's try cosine similarity instead. Yeah, it's still me. Okay, well, maybe inner product will give us a different result. It certainly did. Inner product is like the derpiest one of all of them in this demo. I don't know. So one thing about this the model that I'm using is it's optimized for image extraction, not facial extraction. And so it tends to just find really gross characteristics like there's a middle-aged man in this picture, or there's a cat in this picture, or in this case, I think there's a lot of hair in this picture. And when I was trying in the hall earlier, and all the colorful flags, mocking SpongeBob kept coming up because it was matching the color, is picking up the color from all the banners. So we got 1 minute. I probably shouldn't get a volunteer from the audience. I think that'd probably be pushing my luck. But if you want to do this, we'll be doing it in the Redis booth. I'm going to go ahead and go back to my slides. I've got just 30 seconds worth of things to say here. So. If you want to play with this yourself, and you should totally play with this yourself, it's a lot of fun. You can clone the repo at this GitHub URL right here. QR code's safe. It won't give you up or let you down or run around and take you to some site that it's not supposed to. But you can get there, and it's literally a git clone and Docker compose up, and you're good to go. You want to learn more about Redis and all the vector stuff, you can go to redis.io. The documentation is very thorough. And we have free courses at university.redis.io as well. And we have a Discord server at discord.gg/Redis. So if you're playing with this stuff and you have questions, you can find me there and @ me and try it out. And I'll leave with one slide here. This is a blog post talking about how it scales. We got a good benchmark. We did 1 billion vectors on Redis, and our numbers were really good. So go check those out. And that's what I've got. I'm like a minute over. So thanks a lot, everybody. And hopefully see you at the booth.